Welcome back. This is Dr. Me at the Actuarial Academy. We have an insurance company that insures on an annual basis 500 homes in a particular area where the units are independently prone to hail damage. For any given home, the probability of a claim for the year due to hail damage is 0.01 or 1 out of 100. And for any given policy, if a claim is actually made, the expected loss is $4,000 with a standard deviation of $500. And what we would like to find is the standard deviation of the insurer's total payout for the given year. So this is actually a tricky problem, and I'd like to draw your attention to something important. For any given policy, if a claim is made, then the expected loss is $4,000 with a standard deviation of $500. Okay, it's not making any statement about what happens if there is no claim. Obviously, we do understand what happens. No payout is made, but the point is here, if a claim is made, it's only given statistics on really what the parameters of that distribution is. It has expected payout for a given claim of $4,000 and a standard deviation of $500. And we would like to find, again, the standard deviation of the insurer's total payout for the year. So before we do this, we need to have a few statistical concepts under our belt. That includes conditional expectation, expectation by conditioning, and also conditional variance, because we'll need these tools to actually solve this problem. So conditional expectation, we can define the expected value of a random variable given a certain condition, and that's exactly what this is saying. This is the conditional expectation of x given y. So to give you a little bit of foreshadowing here, we will actually use this fact for the statement that I stressed earlier, that if a claim is made, then the expected loss is given by the statistics I already mentioned. Another concept that's important is expectation by conditioning. If we would like to find the expected value of a random variable x, and we have another random variable in our problem, then we can condition on all the values that it can possibly take on times its associated probability using the conditional expectation here to arrive at the final expected value that's actually unconditioned. Another term we need to understand is conditional variance. Likewise, we can find the variance of a given random variable conditioned on the value of another random variable. And you'll notice that this is the formula for the variance of x, where we've seen that the variance of x is equal to the expected value of x squared minus the expected value of x quantity squared. But here we just merely condition each piece on the value of another random variable, and this condition actually carries throughout that formula. Now, to solve this problem, I've drawn a little diagram here, some pictures, just to help understand how this problem can be solved. Just imagine in the given year we have 500 policies. They're each independent of one another, and given that there's actually a claim made, then the associated distribution has an expected value of $4,000 with a standard deviation of 500. And this is true for all 500 policies. So what's going to happen is for some of these 500 policies, a payout will not be made because there will be no hail damage to the home. However, again, if there is hail damage, say to the, let's say, second home, then the payout will be an expected value of $4,000 with a standard deviation of 500. Now, if, for example, the first home does not have a payout, then and there's no hail damage, then the insurer pays nothing. Okay, so again, this is just if a claim is made. So we are given the probability of hail damage, and so that's nothing but a Bernoulli trial conducted 500 times, where the probability of a claim is equal to 0.01, and the probability of no claim is equal to 0.99. And again, we're basically going to conduct 500 independent Bernoulli trials to determine whether or not a payout is made. And so if there's no claim, then the payout's zero. Again, otherwise the payout is pulled from these individual distributions. So what the problem is asking for is the total standard deviation of the total payout. So that would include instances where there's no payout made. To solve that further, let's actually take a particular policy. Let's just focus on one, and let's let X be equal to the annual amount paid out on a given policy. Okay, just like that. And just to emphasize, we will have two situations occur from X. So X is the actual annual amount paid. So this will include, for that particular policy, where we may not pay out, that is, there's no claim made, no hail damage to the home. And in that case, the payout will actually be 0 with probability 0.99. Likewise, we can have the situation where something else is paid out. Okay, we really don't know what that is. That's stochastic in nature. All we know is that if there is a payout, its mean is 4,000 and the standard deviation is 500. So just to informally make that clear, we'll say the payout is something else. Okay, something we really don't know. It won't be exactly 4,000 every time. It's just the expected value given that there's a claim. But we know something about that something else payout. It'll be with a mean, actually it's a conditional mean, of the expected value. It has expected value of X given that there's a claim. So I'm going to introduce some notation here formally because we're going to use this. So the expected value of X given that there's a claim, we're told is 4,000. That's what's expected if there is a claim. Now obviously, well, not necessarily obviously, but it won't necessarily be 4,000 every time because it also has variability, and we'll write that here, and I'll use SD for standard deviation given again that there's a claim of 500. So for each of these 500 policies, two things can happen. With probability 0.99, nothing is paid out, or if there is a claim, then it's pulled from its respective distribution, as I've drawn here, and it has conditional mean of 4,000 and conditional standard deviation of 500. So let me flip the page here and draw a picture here to illustrate what I just mentioned. The two situations that can occur are nothing's paid out, or if something is paid out, again, it's pulled from this distribution here, where, just for completeness, I will reproduce our parameter here. So this occurs with probability 0.99. So this is our probability of occurrence, and this occurs with probability 0.01. And so we can think of a kind of a mass, probability mass right at 0, occurring 99% of the time, and then something that's pulled from this distribution when the payout's actually made of probability 0.01 as given here. Okay, a little bit informal, but that's okay. I think you understand what I mean by that. And what we like to do is, at least for this particular claim, is find the variance, and then eventually the standard deviation, of the payout, which will ultimately include the 0 as well. Our goal then is to compute the variance of X, where again, X was defined earlier as the annual amount paid on a given policy, because we're just going to pull one out, and then later we'll make adjustments for the 500. Okay, and again, this includes the possibility of no payouts. So the first thing we want to do is compute the expected value of X. Okay, this part's easy, but we'll need it to complete the problem. And we're going to use our conditional expectation to actually find the expected value of X. So the expected value of X, and we're going to condition on whether a claim is made or not. It's equal to the expected value of X given a claim is made, and then times the probability of a claim plus the expected value of X given no claim times the probability of no claim. Squeeze that in there. And we already said that the expected value of X given that there's a claim is 4,000. So if the phone rings, somebody says, hey, I got hail damage, then the person on the other end working for the insurance company is already thinking, oh, it's going to be roughly expected value of $4,000 with a standard deviation of 500. Okay, and the probability of a claim is 0.01, and the expected value of X given that there's no claim, that's trivial. We pay out nothing, and the associated probability is 0.99. So this is equal to 40. That's our expected payout for that given policy. And I think you can intuit your way through this and see why that's the case. we again are looking for the variance of x. We're looking for this piece right here. So let's write out the formula for the variance of x. The variance of x is the expected value of x squared minus the expected value of x quantity squared. I'll notate that without having to put parentheses around here, just like that, squared. Okay, so we're taking the quantity expected value of x squared. This is equal to the expected value of x squared. Now, we don't know what the expected value of x squared is. Okay, this is a tricky part. We can't say it's 4,000 squared because x is a random variable. All we know is its mean and standard deviation. So we really can't compute this piece directly. So this is still an unknown for us here, and so I'm just going to leave it as the expected value of x squared in the hopes that maybe we will be able to compute that later and then plug it into this formula. Now we do know the expected value of x. We just computed it right here. That's 40. So that's 40 squared. So again, we need this. So to this end, let's see what we can do by actually writing out what expected value of x squared is. Okay, again, I'm going to use the conditional expectation formula. It's still valid even for x squared. It's valid for any function inside these brackets. It's the expected value of x squared given, again, no claim times the probability of no claim plus the expected value of x squared given claim times the probability that there is a claim. If there is no claim, there's no payout. So we do know that this is actually equal to 0. Okay, that's deterministic if there's no claim. So we can literally compute 0 squared if we want to and plug that in just like that. And then times the probability of no claim. Plus, now we need this piece here, expected value of x squared, given that there's a claim, and we don't know what that is either, basically for the same reasons that we don't know it up here. So I'm going to leave it alone. But we do know the probability of a claim, and that's 0.01. This is almost like a computer program where you're having to keep calling another function in a subroutine. So now we need this. What we need to do then is use the formula I've given here, the conditional variance formula, and see if we can play with that somehow to generate what we need. Because if you notice in here, we do have the expected value of x squared, which looks very similar to what we have on this page here, where we have y equaling a given claim. And so the hope is that we can possibly solve for this because we're given this, the variance of x given we have a claim, and we also have this piece here, the expected value of x given a claim. So this is nice. So that gives us some hope to be able to solve for that middle piece. Okay, so let me write that out, what I just described. The variance of x given a claim, and I'm using that formula from before, is equal to the expected value of x squared given a claim minus the expected value of x given a claim. We're conditioning this entire formula on the fact that we actually have a claim, and this should be squared. This is really nice because, as I mentioned, we do have the variance of x given that there's a claim. Okay, there's the standard deviation, so all we have to do is just square it, which is equal to, and again, this is the piece that we're trying to solve for, minus the expected value of x given a claim. We have that right there. That's just 4,000 squared. So at this point, when you're taking the actuarial exam, you should say, oh my god, I'm on a roll. This is good. It looks like I'm going the right direction because you have some pieces here and you can actually solve for something now. You can actually solve for this unknown piece, the expected value of x squared given that there's a claim. We've actually found it. It's equal to, and just using a little algebra, we'll bring this to the other side. And so we have 500 squared plus 4,000 squared. So we found our first gold nugget that we can use. We actually have a number we can associate with it. 16,250,000. That's our expected value of x squared given a claim, something that was unknown previously. So now, if you look at this formula back here, you kind of see how this rolls up. We've now found this piece right here. Sneak that in right here. That's that piece right there. Okay, and we're going to substitute this value in for that right here, and then we'll have our expected value of x squared. So looking ahead, once we have that, then we plug it back into this formula, and then we have our variance of x, and we're actually done. So let me turn the page, and we'll work through those steps now. So this implies that now I'm actually going to plug it back into that formula that I alluded to. We can actually compute the expected value of x squared, which is equal to, I won't reproduce the formula, you can look back. That was 0 times 0.99 plus, now I'm substituting in the expected value of x squared given that there's a claim, and times the probability of a claim, which is equal to 162,500, which implies now we can go back and plug it into our original formula to find the actual variance of x, which is equal to, and I'll just reproduce it here just for clarity, expected value of x squared minus the expected value of x quantity squared, which is equal to 162,000, which we found above, 162,500, minus 40 squared, which is equal to 160,900. So we're almost done. Now we just need to put the pieces together and make sure we actually answer the original question, because remember, this is the variance of just one particular policy. So what we're going to have to do is multiply that times 500, because we know they're all independent policies. So now the variance of 500 independent policies is just that value there multiplied times 500. And again, the reason why we can do that, we're basically summing up 160,900 500 times, which is the same as just, of course, multiplying that times 500. That's, of course, the variance. They ask for the standard deviation, so you have to be careful. The standard deviation is just the square root of that, which is equal to 8,969. And that's the final answer. That's the actual standard deviation of the total payout for the 500 homes for the given year. Thank you.